Hi, everyone. Thanks so much for this opportunity. It's great to be back this year and give an update. And for both Ed and I being involved in this project for many years, it's so exciting to be able to see this project progress and advance. So I'm going to give a brief summary of where we are and what the project and company is today. And then Ed has some exciting news to share in terms of all of the work that he and the geology team have been doing over the past year and over the past few years. So a quick overview of who we are. Torngap Metals, we're a privately held company, and our sole focus is developing the Strange Lake Rare Earth Project. Our project is well known because this deposit that we're developing is world-class in terms of its size and quality of the rare earth minerals. Rare earths used to be something I'd have to spend a lot of time explaining, and so it's very nice at this point that most people know what rare earths are and how critical they are to the green transition that we're going through as we combat climate change. And the rare earths that are there's many rare earths, and the ones, of course, that are the key to that green transition are the ones that go in a technology called permanent magnets. And those permanent magnets is what enables high efficiency motors that go into things like EV drivetrain motors. And so we're fortunate with our deposit that we have the 4 rare earths needed for those permanent magnets. And in particular, we're unique because we have the 2 heavy rare earths that are essential for the high performance version of these permanent magnets that go especially into electric vehicles and other applications. And so our goal ultimately is to be the leading supplier of the heavy rare earths and provide security of supply against what China is doing today, which is providing almost 100% of the heavy rare earths. And so our plan is to go from mining to producing separated rare earth oxides that then can go into the permanent magnet supply chain. And we're targeting to be in production in 2028. And we have a lot of work to do. We've been doing a lot of work, but the reason why we think this timeline is so important, of course, that's what the market needs. The EV transition, whether the pace goes a little slower or a little faster, it requires an enormous amount of minerals to be mined, as many speakers have spoken to today. We're very fortunate with this project that we've been able to collaborate with many world-class partners, and as many speakers have talked today, these kind of projects don't advance with a small team. There's many people, many companies, many organizations that need to come together to make a project like this happen. And for us, the stage that we're at, we were very fortunate a couple of years ago to attract an investor, private equity from the US, who saw the potential to address the need for heavy rare earths in particular as part of this green energy transition. And on that investment thesis, put in the largest single investment in rare earths in Canada. And that is what's been allowing us to advance the project really at scale with many aspects of the project, all aspects of the project happening in parallel. The engineering, the geology, the environmental impact assessments, of course, very importantly, our engagement with all of the Indigenous communities that are impacted and we want to partner with on this project. So a quick overview. Many of you already are aware of the project, but just a reminder, we are mining on the Quebec side of this very large Strange Lake peralkali rare earth complex, and doing on-site concentration, and then doing, that's a remote site, and so we've optimized what we do at the mine site and what we'll do at the rare earth separation plant that we're proposing for the city of Sept-Îles. But important and essential to this project is to be able to transport that high-value concentrate from the mine site to the separation plant. And the concentrate that we'll be shipping is going to be containerized, and at that point, rare earths are a very high-priced specialty metal. The concentrate is worth thousands of dollars a ton. And so the importance of the infrastructure to get the concentrate to the separation plant can't be underestimated. And the jobs in terms of construction and operations of this concentrate is going to be significant. But moreover, we would like to be the first of many rare earth projects, and we certainly see the opportunity to develop a rare earth industry in Canada, and particularly anchored in this region that is so rich in critical minerals and especially in rare earths. So we believe our success won't be to get just this project into production, although that is a significant event for the rare earth industry in general, but our success will be if we can grow a rare earth industry, and that with the technology around rare earths that we develop in Canada can be the foundation for growing that for this region. So the track we're on is to have our pre-feasibility study and feasibility study next year. We're already working on the feasibility study thanks to the support we have from our strategic investor. And what we've really been able to do, to step back for a moment, because this project has been around for quite a long time, the transition that we've been fortunate to make is going from understanding we have a world-class deposit to figuring out what is the world-class project that we wrap around it. And really the foundation for that is understanding this world-class deposit. And so foundational to having the project advance to where it is really understanding what's in the ground. And that's why I'm so pleased that Ed is here to share with you today what he and his team have learned about this deposit that enables us to do selective mining, to reduce our environmental footprint and efficiency, and get the interest of the global rare earth market, which is where I spend a lot of my time talking to magnet makers, talking to car makers, talking to wind turbine makers, and this gets them really excited. So I'll turn it over to you, Ed. Thanks.
Great, thanks, Christine. Top button, perfect. Okay, I've been working on the project off and on since 2015. Started with helping collect a bulk sample. At that time, Quest had published a resource estimate in 2014 that was 100% based on geostatistics. We recognized that there was a lot of variability in the grade and the rock units, and that there was the potential to actually isolate a high-grade dysprosium resource within what had been outlined. And then we spent a bit of time, several years, off and on, re-examining the drill core and actually starting to delineate the zones. Now, there's some complex interpretation or observations which end up actually being very simple. Once we got the characterization simpler with, the first presence of things and the last presence, then we started getting contacts, and we started outlining the resource. And then in 2019, we were outlined a preliminary economic assessment with that information in it, and that gave us the opportunity, or then with the funding from Cerberus Capital, we were able to confirm that new geological model. And then but that was just based on the mid-grade material mostly. We still needed to outline the high-grade material. And this past year, we were able to delineate contacts with the high-grade dysprosium material within the mid-grade. So this is a big advancement, so we can selectively mine the high-grade in the early years of the mining and pay back down the capital costs sooner. Now, this is just a quick outline of what a long section of the deposit. Let's see if I can do this. Okay. For people who know, there's Lac Brisson there. So this is a surface topography, the light line. That's Lac Brisson. There's the esker. And the pit design starts about here. And then these are what we're oddly referring to as structural domains. One of the important things with the resource was understanding how the fluids, the granitic, pegmatitic, and later hydrothermal fluids collected. And what we're seeing is that there were these weak extensional zones where there was collection. Now, one of the problems with that is that it looks like there's a lot of episodes. So it opens up and there's collapse structures, and so we needed to sort through all that. And by doing that, we ended up, I'm blinding people in the front row. By doing that, we were then able to, within these mid-grade zones of the structural domain, outline the high-grade dysprosium zones. Now, the fascinating thing about this is that the structural domains that we're calling the main ones, where we can see easily in drill core, were when the granitic material and the pegmatitic material acted, were ductile. So there was a lot of flow structures, we can identify those, and that was a big difference between that and then when it shifts to being brittle. So when it becomes brittle, which is the black outlines here, we start then seeing these infilling zones and breccia. And by identifying that within the structural domain, we can identify the high-grade material. This is just a quick, well, sort of quick, but just to show. In this column here, so we had to go through and we had to identify all the paragenic sequences. I think that was important because there was a lot of times where you call something pegmatite, you call something granite, but it fit into a sequence of events. And then with that, we were able to identify the domains. We had a set of characteristics, and then we could delineate between ductile and brittle zones. And then with that, we could characterize as to whether something was mid-low grade or high grade. Now, one of the things is important is that the granitic material, which is the main host of the rock, hosts these mid-grade ductile structures that we're outlining, where we can readily identify the contacts. And the brittle structures, which are the high-grade zones, are inside this. So we end up, and this is part of the complexity, we end up with rock units that we're delineating that are present throughout, but they're caught up inside a breccia fracturing zone. So, you know, not much different than an epithermal deposit, but it's sub-horizontal, and it has rare earths in it. And there was, you know, it's a fantastic deposit. There's all kinds of alteration, mineralization, new minerals, and there was a lot of emphasis on the pseudomorphic replacements and the alteration events in it. And that was a lot of the descriptions that Quest had focused on in the drill core. But we don't see any enrichment of rare earth elements. So we're trying to find the main zones, and we just don't see that as being important. So that was a big confusion part, because you're trying to identify it, and that's the most difficult to identify. But once we started recognizing the rocks that were created by ductile movement, we then started seeing a sequence of a succession of pegmatite formation, which went from myelolytic to what we're referring to as a pulp breccia, which is kind of the main zone. And this was fascinating because it's not really a pegmatite, but it looks like it moved around. And so that's why we're considering that bit of a collapse structure, because we see, you know, feldspar grains in a matrix of seriate quartz, which likely was not fully consolidated. And we can see flow textures in that. Sometimes it looks like a debris flow. So it's a fascinating thing. But we're not really seeing any inputs and discharge. I'll show some chemistry later. So this looks like it's a closed system. So we see this activation and crystallization, activation and crystallization as the system's cooling. And then down here you see there's this fluorite, the fracture-controlled fluorite. That was another part that was important. It's very dramatic and very fascinating, but as you can see, we don't see any enrichment in it. And then one thing that came up recently in the 2024 drilling was 2 generations of yttrium silicate mineralization, which defines the high-grade material. So this is sort of an early brittle structure, and then this is a later. And the mineralogy looks different, and the grain size is different as well. So yeah, one of the, like Christine mentioned about the partners, one of the great things is Metso is one of the partners, and when we're doing the test work, we have this, you know, it was difficult at the beginning where to focus and as what to do and with the flow sheet, but by making sure things were simple, and then Metso was there with their performance guarantee, that what we were trying to do was something that they could actually engineer and build. So with that, and working with several labs, but currently with SGS, we're able to kind of get the best of both worlds, the best kind of lab performance, as well as something that won't have any surprises when it comes into commissioning. And so essentially we have a multi-stage mag separation, and then followed by a multi-stage flotation. So that's probably the only real complexity we have, is that, you know, we're doing standard mag flotation or mag separation and flotation, but there's multiple steps. And that's part of the, because of the bimodality and the complexities, we have some coarse yttrium silicates, we have finer yttrium silicates, and then Metso is going to be using their Concord cell to help with some of the fine-grained mineralization with it. And then that concentrate gets shipped from Lac Brisson to Sept-Îles, like Christine mentioned. Just to show, yeah, so when it comes to the complexities, one of the things we're finding is when you look at it microscopically, you can get these, you know, really crazy minerals. Some of them are amorphous, you know, fluorine, niobates, phosphates, yttrium silicates. But when you start looking at and compositing the zones, we start generating consistency at that 5-meter bench level within the pit. And here's just an example. We have composites, 3 composites in the at SGS right now. This is sort of the mid-grade, which is more granitic. And then this is the pulp breccia I mentioned before. And then these are the rocks which have a dominantly fracture infillings and brecciation. And so with the mag separation, we can target about 2/3 of the rock and getting rid of that right off the bat. And knowing that, and that was the other problem too, is that knowing there was a lot of different things about where the rare earths were concentrating. But one of the things we know is that the quartz and feldspar for sure are earlier, so we can get rid of those with very few losses. And then even with the pyroxenes and the amphiboles, that is also something that, sure, there's some alteration that's caught up that has maybe some rare earth mineralization, but not enough to make a difference. And then with the yttrium silicates, again, there's so many different minerals and what to focus on. And so here is, again, this, oh, I didn't mention, this is TEMA data. We had a heck of a time with QuemScan data where it really didn't accurately represent the yttrium silicate distribution within the samples. But here we have the TEMA data from SGS, and you can see the green is the yttrium silicates. And with this characterization and then the compositing, we're now starting to get some systematic variation where the stuff that we think is, you know, low mid-grade to high grade. And as you can see, there's not a lot of difference in the modal mineralogy abundance, except for the higher grade having a higher proportion of fluorocarbonates. And based on the data we've been getting over the last several years, whatever we get with the heavy rare earth elements, the light rare earth elements are, you know, 10 to 15% better recovery. So, you know, a lot of the work was focusing on multi-elements, especially in the Quest days, but by just focusing on dysprosium, which is our main pay element, it helps us with the petrology of the deposit and gets us the economic benefit. We can simplify something that's very complex to something that is tangible and something we can characterize better. Now, I'm just going to go through a couple of quick chemistry slides, again, kind of emphasizing this idea that, now this is zirconium on the y-axis in both graphs, and dysprosium's on the x-axis, and neodymium's on the x-axis here. Now, this is rocks from the zones from the granite domain, and you can see, you know, clearly zirconium is following a granite pegmatite variation, and in both the with both dysprosium and neodymium. Now, some of this scatter, and this is where I was saying about the complexity, we have the domains, and they're there, and then the brittle fracturing overprints on it. So these are zones that we start seeing some fracture infillings. You can take something that is low grade, and you can have a 2-3 centimeter fracture in it, and it can become mid-grade very easily. And here is the samples from the structural domain, and then the orange is the pulp breccia. And you can see, again, those units that we were able to break out and substitute, we didn't know at the time, but this was stuff that we could paragenically say this is earlier, later, and we could identify the zones. And again, it's showing a clear non-relationship to zirconium. And then we get into the scatter. And so if you bring all those graphs together, you look at it and you think it's all shotgun. But now with the characterization, so we still have zirconium on the y-axis and dysprosium and neodymium here. And so what's happening is as the fractures are penetrating the zones, they're upgrading it in dysprosium and neodymium. And I think just for the people in the back, this one here is, let's see if I can do this. That is the 500 ppm dysprosium line. So these are all very high-grade dysprosium samples. I think there's a couple other deposits in the world trying to make a mine out of dysprosium, and they're in the 200 to 300 range. So our low-grade material is what other people are trying to make economic. Oop, is that mine? Just a couple more slides. So okay, here's the structural zone, samples from the structural zone, and this is neodymium versus dysprosium. So I was mentioning we had 2 generations of dysprosium, but we also, amazingly enough, the light rare earth elements and the heavy rare earth elements are moving around on their own. And here you can see the oops, how do I go back? These were all associated with quartz veining that we've now identified in the sample, whereas the dysprosium, you get a bit of an increase in neodymium, but not a lot. And then, okay, for the last slide, just coming back to the actual, what we've now characterized the deposit as. This is the same as before, the long section with Black Bisson here, and the main pit here. So now we can selectively mine, and part of the updating of the mine plan currently underway is to focus on these high-grade zones here and find out how much we can feasibly mine, stockpiling the mid-grade, and then processing that later. Thanks.